Hello, this is Team 22057, the Windmill Conversion Project, sponsored by Tucson Village Farms. Here's a visual summary of the project. Let's go further in depth.
Hi, my name's Justin. I'm one of the mechanical engineers on this team. Tucson Village Farms is an urban farm that specializes in community outreach for children. They teach kids how to grow healthy fruits and vegetables, as well as cook them here in their kitchen. This 10-foot in diameter Air Motor 702 windmill was donated to the farm by board member Paul Lindsay.
Hi, my name is Caleb Yoshiyama, and I am the lead systems engineer on the team.
The goal of our Design Day project was to convert an air motor windmill to produce electricity and educate the visitors of Tucson Village Farm using a budget of $4,000. By converting the water pump mechanics to produce electricity instead, the purpose of the windmill now has a relevant use for the farm to generate renewable energy while serving as an educational experience. The scope of our project was very unbounded at the beginning stages of design. With help from our sponsor, the team better defined our boundaries and were able to detail what exactly was expected within our system.
I'm Shane Lawler, the team lead and electrical engineer.
To deliver a quality system, we had to work very closely with Tucson Village Farms to establish a reasonable scope given the limited time and budget provided.
The scope of our system included uninstalling the water pump assembly and implementing a new gear system to increase rotational efficiency, providing a battery system to store and dissipate all generated power, displaying an interactive/educational exhibit for the visitors, as well as providing an inverter so visitors can use the system's generated power. The overall system of our design would be broken down into three main subsystems: our drivetrain assembly or mechanical subsystem, the electrical assembly or the electrical subsystem, as well as our provided educational exhibit.
Hi, I'm Michael Devins. I was one of the mechanical engineers on this project.
To begin our design process, we needed to understand how much power the windmill could reasonably produce and how much of this produced power we would be able to utilize. To get a good idea of how much power output we could expect the windmill to produce, we used the concept of the Betz limit, which is the maximum theoretical power that any windmill could produce. We decided that for our system requirements, that we would accept 10% of this theoretical limit as our acceptable power output to harvest from the windmill. In addition to the Betz limit, we also looked over some experimental data from published sources on the efficiency of the windmills, so we could also get an understanding of how the efficiency of the windmill changes with different wind speeds. Combining the theoretical Betz limit and the data that gave us the windmill efficiency at different wind speeds, we were able to come up with a curve that gave us a good estimate of how much power we could expect from the windmill at any given wind speed. This in turn gave us a baseline to begin our other design processes.
The system was designed to maximize efficiency in Tucson's low wind speeds, but at higher wind speeds, the turbine could produce as much as 700 watts of power. Therefore, it was designed to a 1 kilowatt limit, ensuring all subsystems will function at the 700 watt peak. For similar reasons, we included a 100 amp hour battery. This is far more than the exhibit needs, however, it'll capture the maximum amount of free energy for Tucson Village Farms.
Next up, we'll talk about the educational assembly. This windmill is a great opportunity to teach kids about renewable energy and how electricity is made from wind turbines. There's an interactive portion where kids can rotate a hand-cranked generator to produce their own electricity, and they compare this value with how much electricity the windmill is making and the current wind speeds, all through monitors and LED watt meters. There's also another monitor that shows how much energy they're using if they plug in their phone or another device into the outlet that we have in the exhibit.
Hi, I'm Michael Whitley and I am a mechanical engineer on the project, and I focused mainly on the mechanical assembly. The original mechanical assembly for the windmill was made over 100 years ago. As such, a lot of the designs and CAD models were not available for us to modify. For our mechanical assembly, we wanted to mitigate mechanical losses as much as possible. When initially selecting our mechanical assembly, we decided to go with the direct drive unit. However, we found that the direct drive unit would not apply enough RPMs directly from the windmill to the alternator to produce the required power for the assembly. This, however, led us to the chain assembly, as we wanted to mitigate as much loss as possible.
In order to overcome the shortcomings of the direct drive system, we went back to the drawing board, went through some more trade studies and analysis, and decided on the chain drive system instead. The chain drive system uses a series of sprockets and chains to drastically increase the speed of the alternator so that it's better able to utilize the output of the wind turbine and generate as much power as possible, especially at low wind speeds. Once we had settled on the chain drive system over the direct drive system, we performed another system verification test to ensure that the chain drive would perform to our system requirements. And in fact, it did perform, and we decided to move forward with this system for the final design.
One of the difficulties when designing the mechanical assembly within the nacelle was the actual geometric space that we had. The nacelle seems quite large, but in fact it is significantly smaller than originally planned. We had to go up to the top of the nacelle to acquire the geometry in which our mechanical assembly would fit. And we found that it was quite tight. As such, we had to adjust our chain and sprocket assembly from a 50 type roller to a 40 type roller. Through prototyping and analysis, we determined that a 6-to-1 gear ratio was required so that we would have the proper output voltage to the cabinet.
The electrical subassembly was designed around industry standards for wind turbines, allowing it to safely produce, store, and dispose of excess energy. The energy produced by the alternator is fed through a 3-phase alternating current line down to the base of the cabinet, where a rectifier changes this to one direct current that then charges the battery. The charge controller ensures that the battery doesn't overcharge or over-discharge. If it does sense the battery begin to overcharge, it'll activate a solenoid relay, which then allows the energy being produced by the alternator to flow through a dump load resistor, safely dissipating the excess as heat into the environment. The energy that's stored in the battery is used to power the LEDs and monitors in the exhibit, as well as an inverter. Majority of the electrical components reside in the cabinet at the base of the educational exhibit. This includes a switch that acts as an AC disconnect or an electrical break, the AC-DC rectifier, the charge controller, the solenoidal relay, and an A&L fuse, as well as a DC breaker for safety in service. One of the core requirements of our project is safety. This is why we followed the industry standard of the National Electric Code, specifically Article 694 pertaining to wind turbines. This led us to our system requirements of grounding, proper current reading, and reasonable access for service to the system.
Here is a visual of our final assembly, which includes our mechanical and electrical components. Our drivetrain assembly sits nicely within the nacelle, while our alternator is mounted securely to the original windmill brackets. The slip ring is also pictured here, passing electrical signals and power across our rotating interface. The team was able to successfully complete our goals and satisfy all system requirements attached to the design. We hope to give the Tucson Village Farm a new look into the future of renewable energy and are happy to have educated the next generation. Thanks so much for watching.